Good morning, everyone. How are you today? Okay, welcome to the lecture of the material science. The weekend is coming again, right? So these days we have many holidays and weekends, but it's time to learn. So please, um, before you have a nice weekend, let's concentrate on what you are going to learn uh, with me today. So, as usual, before we go to the lecture, let's recall what we have learned on Wednesday. Wednesday, we start to know the periodic table, right? The periodic table. And then we know there are four traits of the periodic table. So they are atomic radius, electron negativity, electron affinity, and ionization energy. So these four traits are important because if you have a periodical table in your hand, and then these four traits is the information you can get basically from this periodical table. So for example, first one is atomic radius. So atomic radius is increasing from from the top from from the top to the bottom according to this column, right? So all the columns looks the same traits. Increase atomic radius increase because of what? Because the principal quantum number is from 1, 2, 3, 4. So right. So the principal quantum number tells us that uh, the number is related to the size. So the number increasing, the size increase. So you know that the size will increase from the top to the bottom. And the size decrease from the left to the right. Why? Because we are talking about almost the same principal quantum number. And within a quantum number, and then this, for example, lithium, there are 3 protons, 4 protons, 5 protons, 6 protons. And then if you have more protons in the nucleus, that means you have more positive charge. If you have more positive charge, that means according to Coulombic attraction, the electron will be pulled in and closer to the nucleus. That means what? That means the radius will become smaller, right? So this is the reason. This is the traits of the atomic radius according to the periodic table. So the first one. The second one is called is also important. It's called electron negativity. The electron negativity tells us that the range is from 0.7 to 4. 0.7 to 4. The electron negativity tells us that how much this atom likes electron. As you know, fluorine is the one which likes the electron most. And then Francis is the one who doesn't like electrons because what? Because you have, according to S2P6 architic stability rules, then you have extra electron, 1 extra electron, 2 extra electron. You want to get rid of this electron in order to become S2P6 architic structure. Okay, and then this one you have 7 valence electrons, and once you receive 1 more electron, you can get S2P6 architic stability, right? So that means that again, the electron negativity will decrease from the top to the bottom, will decrease. Okay, and the electronegativity will increase from the left to the right. Okay, so this is also another important trait you want to understand, you want to know. Okay, the third one is called affinity. The definition of affinity, electron affinity, is that you have a neutral atoms, and then you will receive one electrons. And this electron, once you get electron, you will become ion. And especially this is an ion, right? An ion, and plus energy. Okay, so this also is the traits for you to understand. But there are not strict rules for this case, so I don't want to put more effort on this trace. So the last one is called ionization energy. Ionization energy tell you that in order to become cation, in order to become an ion, and this one ionization energy is you want to become cation. And cation means that you want to take one electron away from this atom, and this one will be, the atom will become cation. Okay, and this require energy. This require energy. So the energy we learned is called the one we want to understand is photoelectron spectroscopy. Okay, and I hope you remember this. This is important. We call first ionization energy, and this is the trace. I already explained this to you, and I want to let you understand this. And this might be in your midterm exam paper. Okay, this question might be in your midterm exam paper. So please remember this. So in order to measure the ionization energy, this is the equipment we call photoelectron spectroscopy. It depends on whether the source of the photon is X-ray or ultraviolet. You have different name, right? You have different name. It can be called XPS or UPS. And this is the equipment to tell you that the energy, according to the conservation of energy for the photon and for the electron. And you can get the fingerprint of this bonding of the elements, which show you the bonding energy. Okay, and in the end of the last lecture on Wednesday, we stop here. And here I want to start from here today. Is that for the ionization energy, you know, in the case of lithium, you have 3 electrons, right? 3 electrons. So the outer electron, this energy is increased from the left to the from the right to the left. So this is the number of this is the value of the energy required for taking out one electrons from the atoms. Okay. So the unit of this is megajoule per mole. Okay. So this is 13.6 electron volt, 1 electrons, as you know. This is according to Bohr atomic model. And helium has 2 electrons, right? And then as well, the intensity will be double compared to this one. You see that this is 1 electron, this 2 electrons. The intensity of these inner electrons in the inner shell will be about the double of this outer electron in the outer shell. So there are 2 electrons, and then the average ionization energy is about 2.37 total. And then for the lithium, there are 3 electrons. So the first electron in the outermost shell, the energy required for ionization is about 0.52 electron. That means what? That means about 5.2 electron volt, something like that, right? Okay, and then for the inner electrons, this is 1s, right? 1s2, 2s1. So for the inner electrons that require more energies, as you can see, this is 0.52 megajoule per mole, but the inner electrons require heavy energy, very high energy, which is about 6.26 electron megajoule per mole to take out 2 electrons away from the inner shell of the atoms, right? Right. So the information we can get is this is 1s electrons here, and as you can see, the 1s electrons increase the energy increase. Why? Because, for example, for a boron, there are 5 protons inside. So the 1s electron will be pulled in and closer to the nucleus. And when you want to take it out, it requires more energy, right? That's why the energy increase like this. 2 protons, 3, 4, 5, and 5 protons. Of course, the 1s electrons require heavy energy. Okay, so more proton, tighter bonding. And these are the 2s orbitals electron. I should say electrons in 2s orbitals. Okay, this 5.2 electron volt, 9 electron volt, 13.6 electron volt, something like this. Again, you follow the trace, right? You follow the trace. In proton increase, the bonding energy increase. And this one is 2p electrons. So as you can see, for the boron, there are 5 electrons, which are 1s2, 2s2, and 1p1, right? So this electron require less energy for the ionization. Okay? And you see that the energy increase from outer to the inner shell. So the ionization energy of the electrons in shell M is much lower than that in the K shell K. So this M shell, this K shell, of course, you know the energy required is less. For in the case of boron, the intensity of 2p, this one, is about half of 2s. That means 2s, the 2 electrons, the intensity is about double of the 2p. It makes sense, right? Okay, this is the second example is this: carbon, oxygen, and neon. As we know, carbon has 6 protons, oxygen has 8 protons, and neon has 10 protons, or 10 electrons. And then energy increase from the right to the left again. So as you know, this is 1s, and you know that increasing the proton number and the energy increase. And then this 2s, and this 2p. And you know, because carbon has 6 electrons, so as you can see, the intensity is almost the same here. But oxygen has 8 electrons, so 2, 2, and what? And 4. So this intensity is about double of this 2s. 2p intensity in 2p is about double of the energy in the 2s. Okay, and this one will be the triple, right? So electron IE is ionization energy for short. Okay, IE of the 1s is much greater than 2s and 2p. That's what we already know. Okay, so in the case of carbon, 1s, 2s2, and 2p2 is about the same intensity. And then oxygen, the intensity of 2p is about 2 times greater than the 1s and 2s. No problem, right? And this is triple. Right, so the important thing we want to know is the rules of the electrons in chemical reactivity. As I hope you already know that the chemical reactivity is always related to the valence electron, nothing more than this. So you have valence electrons in A atom and the valence electrons in B atom. There is some relationship or chemical reactions or electron exchange. That means it's called chemical reaction. So there is a huge differences between the energies in the outermost shell and the inner shell. As you can see, the outermost shell, the energy is low compared to inner. You know, inner is very, very high. And this is not stable. And this is very, very stable because you want to take an electron away from this shell. This requires heavy energy, right? 286 electron volt. This is too much. So the electron in the outermost shell are less bound. So this is require less energy. So you don't need to spend too much effort to take out these electrons away from the atom, right? So chemical reactivity determined are only by electrons in the outermost shell. We call valence electron. So there's a link between chemical reactivity and the valence shell. Valence shell electrons. Okay, and we already learned about valence electrons. So I don't want to waste your time here. So I just quickly skip. So for the boron, there are 3 electrons, right? Valence electron, and silicon has 4 valence electrons, and antimony has 5 valence electrons. As you can see that 2s2, and where are these 2 electrons? This is 2s2, 2p1, this 3s2, 3p2, and this 5s2, 5p3. Right, let's recall what we have learned last week. This is the numbers of the valence electrons in a group 1a, 1, group 2a, 2. And we have this, what is this called? Modified d electrons, right? Modified d electrons countermeasure. Right, okay, and then group 13, or sometimes we call group 3a, 4a, 5a, 6a, 7a, and 8. That's a different definition. Right, okay, so now the question is, what if we know the electron we want to take out, or they are very reactive electrons, for example, like silicon, there are 4 valence electrons. And if we want to take out these 4 valence electrons, what's the energy required? Or what's the energy required for these 4 valence electrons? And here, there's a term called average valence electron energy. So for the first ionization energy, we know that you take out 1 electrons away from this atom. For example, in the case of this is silicon. So, and this is not difficult to understand because we use instruments to find out, right? We do the experiment to find out the energy required. And another term is called average valence electron energy. We call AVEE for short, average valence electron energy. Okay, so this is the energy required to take out 4 of these electrons. And this is relative reactivity of the element. So this energy is related to the reactivity for the element. Okay, for example, for the magnesium, there are 2 valence electrons in 2s orbital. The AVE of these 2 valence electrons are defined like this. There are 2, okay? However, for oxygen, there are 6 valence electrons. And you want to know the average valence electron energy of these 6 electrons. And for the magnesium, you want to know the 2 valence electrons, average valence electron energy. So the definition of this is like this. For example, like oxygen. So you have 2 ionization energy in 2s orbital, 2 electrons, right? And you have 4 valence electrons in the 2p orbitals. So you plus this energy and plus this energy together, and you divide it by 6, why 6? Because there are 6 electrons, right? So that's why you get average valence electron energy here. So as a result, the energy required for oxygen AVE is about 1.91 megajoule per mole, and which is about it's about 10 times, right? So that will be 19.8 electron volt, roughly. So we know that oxygen, the AVE of oxygen is about 20, for example, it's about 20. Okay, and this is the number in the periodic table, and for this is first ionization energy, which is different. Some of the numbers in the periodic table tell you first ionization energy. Some of the table in the periodic table tell you the AVE, average valence electron energy. So you need to realize it's different. Okay. So again, this is another periodic table tell you the AVE here. So as you can see, for the metal, AVE is low. For the non-metal, AVE is high. Why? Because it's difficult to take out electrons, right? You need to take a lot of numbers of electrons from the non-metal. But for the metal, in this part, you just take 1, 2, it's easier. And it's easy to reach S2P6 ATEX structure, right? So around in the metal, I don't want you to remember precisely, but you just remember roughly AVE is less than 11 electron volt. And for the non-metal, the AVE is larger than 13 electron volt. For example, oxygen we just learned, right? It's about 20 electron volt. So between metal and the non-metal is called semiconductor. And we call semi-metal. The AVE will be between 11 to 13, right? Okay, 11 to 13. So AVE for metal is less than 11. AVE for the non-metal is larger than 13. Okay, for the others, they are between 13 to 11 electron volt. Okay, right. So this is metal, semiconductor, and non-metal. So you know, in the periodic table, metal contain about 75% of the metal in the periodic table. The rest of the 25% are semiconductor and non-metal. So we know that in the metal, in the part of metal, is AVE is less than 11 electron volt. When the AVE larger than 13 electron volt, the electrons are tightly held. So that means what? The poor electron donors, but the good electron acceptor. So it's difficult to take out the electron, but easy to receive electrons for the non-metal. Okay, and for the electron, for the AVE between 11 electron volt and 13 electron volt is called semi-metals. Okay, meta-alloys. Okay, for the noble gases, it's non-metal, but it's chemically inert because it's H2P6, right? Right, so this is what we called stable ATEC. ATEC, OCT means 8, right? It's 8. So that means S2P6, that means there are 8 electrons in the outermost shell. So the photoelectron spectroscopy, we realize there are many gases has a S2P6, we call stable ATECs, and they belong to the noble gases. So noble gases are these gases, chemically inert, and all have the electron structures of S2P6, except helium. Okay, helium has S2 only. So there are 8 electrons, and the shell is full of electrons. And we call stable ATEC, or ATEC structure. Okay. So, so all the chemical reactions try to make atoms become R-tex stability or stable R-tex structure. Okay, it require the chemical reaction require to have electron transfer, and this is what we call ionic bonding. We are going to talk about this topic very soon. So important thing is that S2P6. Right, so this is the summary of our lecture in section 2.4. We learned from today and on Wednesday, we learned the trace of periods in the periodical table. There are 4 terms you want to know. The first one is atomic radius, second one is electron negativity, the third one is electron affinity, the third one is ionization energy. And the second topic we learn is measurement of the ionization energy. We use photon electron spectroscopy, okay? We call PES for short. So it depends on different sources. It can be X-ray or it can be ultraviolet light. We use XPS or UPS for short. Okay, and then today we learn ionization energy, which are including first ionization energy. Okay, and the rank of ionization energy from inner shell to the outer shell increase from the energy increase from the inner shell to the outer shell. Energy decrease from the inner shell to the outer shell. And finally, we learn AVEE of the metal, semi-metal, and the non-metals. Right. Okay, finally, this is the table in the wiki, in the internet. As you can see that this is the abundance of the atoms of elements. Okay, if you use standard, for example, like silicon here, and you can see that elements in this part are very abundant. So you can find this a lot in the Earth, in our planet. But element here is not a lot. Okay, and does anybody want to tell me what's wrong with these figures? Does anybody want to tell me what's wrong with these figures? There's something wrong. Can you find out? I told you this on Wednesday. Anybody want to tell me? Yes, please. Thank you. Very excellent. I'm very happy somebody learned from me. Okay, you cannot have a line between these two elements, right? Because if you have a line between these two elements, that means there's something in the middle. But as a matter of fact, there's nothing in the middle, because this is quantized, it's number, right? So there's no element between lithium and beryllium. So you shouldn't have a link between this. Anyway, but this is in the wiki, in the internet, but I just take it out. Anyway, you know that in the future you need to know this. Okay? And another information here is that this is a semi-log plot. Does anybody want to tell me why they use semi-log plot in this case? You know, this is compared to this element is about 10 to minus 3 older, and this is 10 to minus 6, 10 to 6. If you use non-log plot, what happened? You have to make a scale very, very large, very high. Does it make, can this show you, is it easy or is it okay to show like this? You know, there are 9 orders differences for the oxygen and like Ru, right? And gold, right? So there are 9 orders differences. So the reason you use the log plot in the y-axis is you want to reduce the size. It make the figures looks nicer, right? Looks nicer. So this is called semi-log plot. And you know there's a log plot, right? Okay. However, if you lay the tray, you can make an equation to predict this for the semi-log plot or log plot. I hope you still remember we learned this when you are in your first year, okay, in my lecture. Anyway, Nowadays, you can find many periodical tables. This Christmas periodical table. Okay, that's it for the section 2.4. In England, today is called Peel's Day. You know why it's Peel's Day? Piece of earlier, tomorrow Saturday. Everybody want to go home and go to have fun as early as possible. Okay, but your mind at this moment should be in the classroom. Okay. You know what did they call on Monday? Monday is Blues Day. Blue Day. Blue Day means that your mind is very blue. Your heart's still on Sunday. You don't want to come here to have lecture and to go to work. So Monday is Blue Day, and then Friday is Pierce Day. Okay, so anyway, I need to work tomorrow and the day after tomorrow. So nothing different for me. Right. Okay. Now let's move to the section 2.5. We finished to talk about atoms itself, including the electrons, proton, neutron, and especially focus on the atomic model and periodical table. And now we want to move to another topic, which are the topic of two atoms together, or atoms together. But to make it simple, we start to discuss two atoms, the interaction between two atoms. So this is called atomic bonding in studies. So there's something related to these two atoms which are very close. So this is called bonding forces and bonding energies. So there's an attraction between two atoms which are very close to each other. And if it's related to the chemical reaction, this is called primary interatomic bonds, or sometimes we call chemical bonds. And if there's nothing related to the chemical reaction, we call physical bond, or we call secondary bondings or van der Waals bondings. And if you put this together, you notice the second topic and third topic, and you will understand what molecular looks like. Okay. So first of all, let's move to 2.5, bonding forces and energies. So we are talking about these two atoms, and between them there's a force attract each other and bind them together, and energies. So first of all, bonding energy. The second one is first one is bonding force. Second one is bonding energy. And different types of the bondings. Right, the first one, bonding forces, is that, to understand of many of these physical properties of the materials is predicted on a knowledge of the interatomic forces that bond the atoms together, how they bond them together. Of course, now it's called ionic bond, magnetic bond, and covalent bond, right? But before we move to that topic, let's have a basic knowledge about this. The bonding forces are bonding force interaction between two isolated atoms. So at a large distance, interaction is negligible. That means if these two atoms are very far away to each other, and you can neglect the forces and the energies. However, if they are very close to each other, and there are two types of the forces. The first one, of course, is called attractive force. The second one is repulsion force. These two atoms might like each other, might don't like each other. So they like each other, it's called attraction force. They don't like each other, it's called repulsion force. And then the net of the forces are equal to the attraction force plus repulsion force, right? So when the force, attraction force and repulsion force balance is equal, so the two atoms will stay steady state, will become steady state. It won't be pulled apart, it won't be too close, and at that time it's called balanced. So the balance when the attraction force and repulsion force become zero, right? There's no problem about this. So let's assume there are two atoms and they are very far away in the beginning, and how do they close to each other? So this is the plot tell you that for the x-axis is interatomic separation, which is the distance between two atoms. Okay, from zero is close, is the same position, right? Which is impossible, and is very far away from each other. And the y-axis above zero is called attraction force. Of course, it's positive, and the line below zero is called repulsion force, which is negative sign, right? Okay, so you have two atoms. In the beginning, they are very far away to each other. And once they get closer and closer, there's some kind of attraction between each other. Okay? And when they close to each other and close to each other, the force will increase. Like this. It makes sense to you, right? It makes sense. But when they are very far away, the force is low. And when they close to each other, the force increasing. This is called attractive force. Okay, and then how about repulsion? Repulsion means that when they are very far away, according to Newton's law, they are very far away, they don't have force. But when they close each other, they start to have force. They always have force attract each other. But for the repulsion, it's not. It doesn't look like this. It will stop in some certain position. So for some certain position, it starts, but it increases dramatically, very fast. So this is called repulsion force. And in the previous slide, we know the net force will be the attraction force plus repulsion force, right? So if you put these two lines together, you will get a net force plot. So how can you get these two together? Very easy, right? So for this one, this is called net force. So according to this plot, the net force is like this, increasing the force, increase until a certain point it starts to decrease. Why? Because the repulsion force is too strong. For example, if these two atoms are very close, you cannot close anymore, but repulsion force will push it out. It's like a magnet. Okay? So this is called net, the line of the net force here. So there are some important things I want to share with you. So when this line, the net force, this line reach to the distance, the force of zero, what does that mean? The net force is equal to zero, right? So repulsion force equal to attractive force. And then two atoms will stay in this position. Am I right? It cannot go further. Why? Because repulsion force push it out. You cannot go far. Because why? Because attraction push the atom in. Right? So the atom will stay here between this distance. And this is called equilibrium spacing. Ladies and gentlemen, I want you to remember this term. Equilibrium spacing, R0. R0. Normally it's about in the scale of Armstrong or 0.5 Armstrong, something like this. Equilibrium spacing. So two atoms were very close, and the distance between these two atoms is called equilibrium spacing, and it's about the scale of Armstrong. Okay? In this case, it depends on different atoms. It can be hydrogen or molecules. It can be oxygen molecules. So the distance are different, depends on the bondings. In this case, it's about 0.3 nanometer. It's about 3 angstroms. Okay, so how about bonding energy? Energy is the summation of the force times distance, right? So if you have force and you have distance, you can do the summation, you got energy. So as we know that for atom system, the net energy will be the summation of the force times distance. And from the infinity to the r, r is the distance, right? And then because we know the net force is equal to attractive force and the repulsion force, that means what? That means you can make this equation become like this. Am I right? I'm right, right? Okay. And so you want to do the summation from very far to very close for the attraction, and also from very far to very close for the repulsion. And as you know, this will be attraction energy and repulsion energy. And because you do the summation from larger number to the small number, so this summation will become negative sign, right? And then this one, because it's negative sign and this energy, this force is negative sign, so it become positive, right? Become positive. So if you want to replot these figures using bonding energy, this will change to this will be the opposite. Attraction force and repulsion for the plot will be opposite. So as you can see, we change from, this is force plot, this is energy plot. So energy versus interatomic separation curve, it will become like this. So this is the repulsion energy from negative sign to become positive sign. And this is attraction energy from positive sign of the force, attraction force to become negative sign of the attractive energy. And this is a summation. It's a net energy here. Okay, and there's another important terms here. It's called equilibrium spacing. It's called bonding energy. As you can see, this line reached to here and the energy reached to the lowest energy. Lowest energy means what? Means it's most stable status for these two atoms. And this E0 is called bonding energy. Ladies and gentlemen, I want you to remember this term, bonding energy. The energy at the minimum point, which is energy is very, very low. The lowest energy. This is called bonding energy. Okay, so you learn two terms. First, equilibrium spacing. Second, bonding energy. Okay? And of course, in this distance, here is about equilibrium spacing, right? Equilibrium spacing. So at this point, you have equilibrium spacing and bonding point, bonding energy. Right, and just put these two plots together for your information. Attraction, the net force like this, and the net energy like this. So another way of the explanation of the bonding energy is the energy that would be required to separate these two atoms to an infinite separation. So this bonding energy is the energy required to put this together, right? So, but if you want to take it out to an infinite distance, and this is also called bonding energy, right? Okay. How about solid material? Solid material is different because, when we talk about bonding energy, we only talk about these two atoms together. But if you have atoms, like 10 atoms, 100 atoms, 1,000 atoms, these atoms will have interaction between the atoms next to this atom, right? It can be not only one, it can be 2, 3, 4, 5. So this is for the solid material is like this. So the bonding energy the energy that will be required to separate these two atoms on an infinite separation, that's what we just learned. However, for the force and energy interaction among many atoms must be considered for the solid material, not for only two individual atoms. Okay, so the magnitude of the bonding energies and energies interaction separation curve vary from the materials to materials. Both depends on types of the atomic bonding. The type of atomic bonding is what? Is ionic bond, metallic bond, or covalent bond. So this information tells you that this curve is just a basic knowledge for you to digest. This curve can be like this. It can be like this. It can be like this. It depends on the different type of the atoms. Okay, but there's two things for sure. Is you always can find out the equilibrium spacing and bonding energy. Okay, so the property of the materials it can be related to this curve. So the number of the material properties depends on what? It depends on the bonding energy, which is here. If your bonding energy is high, that means it's difficult to separate these two atoms, right? Okay. So it also depends on the curves of the atomic, the curve shapes and the bonding types. That's what I just told you. So here there are two examples. The first example is melting points. Melting points. For example, if your curve, for example, if there are two type of atoms, let's say atom A and atom B, and atom A, the curve is like this, right? For the atom A, curve B atom is like this, which has a lower bonding energy, higher bonding energy. For B, bonding energy the bonding energy of A is lower than the bonding energy of B. Please tell me the melting point of A and melting point of B, which one is higher? Which one is higher? You know, if melting point means what? If you think of melting point, you think of boiling point. Melting point means what? The atoms, the distance between the atoms will be far. Why? Because the density of the solid is higher than the density of the liquid and the density of the what? Gas, right? So that means you want to pull atoms away to each other, and it requires energy, right? So require energy when you hit, for example, if you have an ice cube. Once you have an ice cube, you give energy to this ice cube. The ice cube will melt. That means what? Molecules of the water, H2O, pull apart to each other, right? Okay, so for the melting point, that means if you have larger bonding energy, you are higher temperature, melting temperature. So for the case of the atom B, which has higher bonding energy, the melting point will be high, right? Okay. And another case is called mechanical stiffness. So it depends on the force curve shape. Force curve shape, I told you like this, it can be like this, or it can be like this. And we are going to talk about this in chapter 4, I think. Right, so the type of the atomic bond, interatomic bonds, there are two types. The first one is called primary bonds, or we call chemical bond. Involve chemical reaction, that's why we call chemical bond. And second one is called physical bond, physical force, or secondary bond. So between these two types, chemical or physical. So let's take a look of the chemical first. So chemical, the bond involve valence electrons. So it has to be involved valence electrons. This is called primary bonding or chemical bond. So the nature of the bond depends on electron structures of the constituent atoms. It depends on different types. It also depends on how many protons you have. The rise from the tendency of the atoms to assume stable electron structures, inner gases, by complete filling the outermost electron shell. So anything related to the chemical bond is always related to the electrons in the outermost shell. And it need to become stable electron structure, which is RTEC stability, right? RTEC structure, right? Okay, so there are three bondings. One is chemical bond, ionic bond, covalent bond, and metallic bond. We'll go through this one by one. Okay, and for the secondary bonds, so rise from atomic molecular dipoles. There's nothing to do with valence electrons, but related to the yes. I'm sorry. They're always related to the valence bond, valence electrons. But if the valence electron has interaction to exchange or transfer, that means chemical reactions. But if the electron is induced, then it doesn't mean there is no chemical reaction. But in this case, we call dipole. I make example for you. I don't know this appropriate example or not, but you know, when you get married with your girlfriend or your boyfriend, you can regard this as a chemical reaction, for example. But if you are induced by a girl or by a boy, you like each other, it doesn't mean you will become a couple in the future, right? So this is kind of dipole. Well, I don't know this is appropriate example or not, but anyway, I just want to let you know that there are two types of forces. Okay, and dipole is very interesting. Actually, it's kind of, you know, when you fall in love, you know, it's difficult to explain. Anyway, right. So weaker than the primary bonds, but influence the physical properties of materials. It's an interesting topic. We are going to talk about this in next week, I think. Okay, secondary, our physical force, van der Waals bonds, and hydrogen bonds. Right, these two examples. Okay, so let's go to the primary interatomic bondings. The first one is ionic bonding. Right, so let's go to the very, very beginning of the principles, is formation of ionic bonding. You know, when we talk about ionic bonding or any chemical bonds, we always think of stable RTEC or RTEC stability. Okay, so how do we make sodium chloride? You know, sodium chloride is salt, right? It's kind of salt. And we just think of one sodium atom and one chlorine atom, and they become sodium chloride. So for example, the sodium there are 11 electrons, right? So it's 1s2, 2s2, 2p6, and 3s1. And we can use this. We can use inner gas like neon and 3s1 to represent sodium. So as you can see, the sodium is easy to lose one electrons because this become what? If you lose 3s1 electrons, you become 2s2, 2p6. And the energy required to become this is 5.2 electron volt only. Okay? And this is become neon. Electron configuration become neon, right? And it's very stable. An electron here, you know, if you release the electron, you need something to receive you. The electron needs somebody to receive. So need an electron acceptor. In this case is chlorine, right? Chlorine we can use neon and 3s2, 3p5. So that means what? Need a electron acceptor if this require 1 electrons. That means the chlorine, ladies and gentlemen, remember this is in the gas phase. Gas phase means what? There's no interactions. There are not many atoms surrounding. There are only 2. We only consider 2 only electrons. And this can become chlorine anion. The energy required is 16.5 electron volt. I mean, AVE is very high, so you cannot take 7 away, right? You cannot take 7 away, electron away. So this become argon. So it's wonderful if you have one donor and one acceptor, and they suit each other, right? One like electron very much, one doesn't like electron very much. So as a result, these two can get together. Okay, so you might think, well, Professor, what's going on? This is in a gas phase. This is in a gas phase. And the cation and the anion is in what phase? What is this? V stands for vapor, right? Does anybody want to tell me the definition of vapor and gas? I told you this when you are in the first year. Anybody? 0.5 points. I'm sure most of you forget the definition of vapor and gas. 1 point. No. You know, there's a line. Above the line we call gas. Below the line we call vapor. When you have H2O, you call water vapor, right? You call water vapor. Have you ever called water gas or gas? H2O gas. What's the line here? I don't want to tell you. Please go home to check your lecture note. Okay, there's a line between gas. What do you call it gas? When you call it gas? When you call it vapor? Okay, so you know we do the electron transfer to achieve the stable electron configuration. Well, you might be able to ask ChatGPT. You know, ChatGPT might not be able to tell you the correct answer, but it tell you roughly. Somehow it's wrong. Sometimes it's wrong. Okay. You know, in this university, we are creating a GPT called CCU GPT. I have a team to work for this. We call CCU GPT. The CCU GPT give you the correct answer. It doesn't tell you any wrong answer. Okay, we are working on this. For you, that's what we call 24 hours teaching assistant. Anytime you can ask. At night, in the middle of night, in the very beginning of the day. Okay, so 24 hours teaching assistant. And CCU is going to get famous, right? Because we are the first one who is doing this kind of project. But we are leading, but not the first. We are not the only one. Anyway, right. So in the previous slide, we are only talking about 2 atoms together, but you know, sodium chloride is a kind of crystal. It's not only 2 atoms. It's not only sodium and chloride. Sorry, sodium and chlorine becomes sodium chloride. Okay, so this related to the ionic crystal formation. How do you make 2 together, and how do you make a lot of ions get together and become a huge crystal? So, you know, this is the first stage, right? First stage, you lose 1 electron, you receive 1 electron, you become the vapor form. This is related, we call electron transfer. Electron transfer. The reason we got electron transfer is because the both atoms want to get stable attack. So here I just want you to give you a roughly idea is that this is the atoms, the size of atoms. Okay, and then once you become cation and anion, the size of the atom will change. So the size of the cation was smaller, of the sodium will be smaller. Why? Because you lose 1 electrons. Okay, and electron configuration is stable and become n equal to 3, become n equal to 2. The principal of quantum number changed. And then chlorine atoms become chlorine anion, and the size of these anion increased. Okay. And then these two vapor become a sodium chloride vapor. And then please use your imagination to think of this. It's not easy, but please think. Okay, so they're closer, they're a little bit closer, and then the electron exchange, transfer from sodium to chlorine. So you have mobile opposite charges. Why? And they get together. Why? Because of covalent force attraction. Because positive and negative attract each other, so they get together. So first of all, electron transfer to let both atoms have attack stability, and then they attract each other because of Coulombic attraction. And then once you have a molecular, you have many molecules, and you become a solid. By what? By Coulombic forces, right? Because you have this one molecular, you have these molecules, and these two molecules will attract each other because of what? Negative and positive charge, Coulombic forces. And this is called ionic bonding. Ionic bonding. And you might have a question, Professor, why this doesn't make a line only? Why this make a cube? Why it doesn't make another shapes? Why it doesn't become a sheet or a line only? Why it become a cube? We are going to tell you this very soon. It's called Madelin constant. Okay, so at this moment, just remember it become a regular arrays for all directions, for the x direction, y direction, and z direction. It can pack like this because of nature, because of we are going to talk about Madelin constant. So sometimes it can become a size of like a hexagonal structure. Sometimes it can become a cube structure, cubic structure. Okay. So anyway, it will become an older solid. And this is what we call crystal. You know, when you have a salt at home, you have food, you need salt, right? This is sodium chloride. So let me have quickly summarize. This is formation of the ionic bonding, neutral become cation and anion. It involves electron transfer, okay, to become stable atom. The second one is that second step is cation and anion get together because of Coulombic forces or Coulombic attraction, and it become molecular. And step 3 is that molecular become moleculous and become a crystal. By what? By Coulombic forces of the attraction without limit. You are going on. Right, so modeling of the ionic bonds is like this: net plus net minus, and Coulombic force attraction and become this net plus and net minus. Okay. However, as you know, you might say, wow, Professor, this is the negative, positive charge, negative charge, but they all have electron inside, right? So they'll get repulsion anyway. They'll get repulsion. But as you know, there's a repulsion force and attraction force, so they get together, they will have a net force. That's why we have the equilibrium spacing and the bonding energy, right? So this is the one. Put together, you can regard this become cation and anion, or two atoms. So let's quantify this energy. Like electron energy of attraction will become the Q1 times Q2 divided by 4 pi epsilon r, which is related to the distance, right? Okay. And then if you put the Q1, the charge of sodium and charge of chlorine, and you can have one charge or two charges, and you become like this. For example, of sodium chloride, this is two charges. So this is the energy of the attraction. How about energy of repulsion? Energy of repulsion is like this. We don't have time to talk about this, but this is B divided by N power R power N. R is distance. N is the integer number, which is from between 6 to 12. B is a constant. So when you put this together, you will get this curve. The curve in red color. Okay, when you close to this, and then this sodium chloride and sodium chloride get together, this has got equilibrium spacing. Equilibrium spacing and bonding energy. Okay. So this is the cartoon to show you that if they are too far, for example, this is the curve here. R is about 600. This is picometer. Pico is 10 to minus 12 meter. So sodium chloride too far, this is the energy. And if it's too close, this is the point here, this is the energy, okay, which is not stable, you know that. And when you reach to the radius is about 236 picometer, it becomes stable. Sodium chloride will stay here. Right, I think we run out of our time today. I will stop here. So I hope you enjoyed the lecture today. I hope you learned something from me today. And I wish you have a nice weekend.